Just to check, those of you on Zoom, can you hear me? Please type something in the chat. Okay, good. Right. Hi, hello. Welcome to the Graduate Maths Program 2021-2022. This will be our, I suppose, third to last talk of this year. Next week we will be having Y draft, and the final week I might give a talk or not. I don't know. So anyway, last week we heard from John about quadratic and cubic reciprocity. So it's somewhat related to number theory and especially the algebraic number theory. And today we'll be still having some number theory talks, and it will be analytic given by our PhD student Marius. And well, let's have Marius then.
Hello guys.
Let me turn this off.
Oh yeah. Well, thanks for inviting me. So I'm Marius, I'm going to create number theory. Today I'm going to try to explain to you basically why it makes sense to mix number theory analysis through some examples like prime numbers and Riemann hypothesis, and if we have time, some other stuff as well. So yeah, I guess it's a bit weird because analytic means something continuous, and we are used to number theory as something discrete. So those things are supposed to be polar opposites. And what I'm going to try to explain to you is actually that if you view number theory in the right way, it makes total sense to think about it in an analytic way. So one of the main objects in number theory, as you know, are the prime numbers, like the numbers 2, 3, 5, 7, 11, and so on. People were interested in those numbers in ancient times, mainly because they have some weird patterns, they have some very interesting properties, and they seem to be so easy to define, but it's interesting that it's difficult to prove things about them. For example, Euclid proved that we have infinite many primes. And people after Euclid were wondering, okay, we have infinite many primes, but how fast does that number grow? So we can see that up to 10, you have, so you have four prime numbers up to 10. And I mean, you can go on and say that up to 20, you have 7 numbers, yeah, 6, 8, and so on, and up to 100 you have 25. So I guess people were interested to find the pattern in how that number grows. Are you guys laughing? So it was Legendre first who thought that this number here, which by the way we call pi of x. So pi of x is defined as the number of primes smaller or equal to x. So it was Legendre who first conjectured that this kind of looks like x over log x. So you have something completely number theoretic here, the number of primes more or equal to x. And here you have something that looks suspiciously analytic, because log x is something that you find in analysis, not a number theory usually. So people started wondering if there is a way to show that by finding a relation between analysis and number theory. And this was proved after about 100 years. So that was in 1797, I think. And it was proved in 1896 by, it's pronounced Poussin and Arnold. So this is what they call the prime number theorem. It's the main result of analytic number theory. From that, you can get lots of other results about prime numbers. And what I'm going to do, at least for now, is I'm going to try to explain to you how those people used analysis in a very natural way to prove this theorem. So I'm gonna write this down here. And actually, it turned out that a much better approximation was this, which is slightly similar, slightly different. We can see that why this is around x over x, because you have a length around log x, and what's inside is around 1 over x. So that's what we are going to try to prove. Just a remark in case you haven't seen that before. So when we say that two functions fx and gx are asymptotic to each other, what we mean is that fx over gx tends to 1 as x tends to infinity. Okay, so that's what we're going to try to prove, that the ratio of those two things tends to 1. I guess the fundamental property of the prime numbers is that every integer can be, every natural number can be written as a product of primes in a unique way. That's what we call the fundamental theorem. Of Archimedes. Which says that every natural number can be written uniquely as a product of prime powers. So it would be nice if we could express this theorem in a single equation rather than in a statement. And one way to think about this is if you think, for example, of this product here. So if you simplify this thing, you're going to get basically all the possible products of one thing from here and one thing from here, right? So that's 1 plus 2 times 1 plus 2 times 3, and so on. So it's basically the sum of all the things of the form 2i, 3i, 3j, where I is from 0 to 2 and j is from 0 to 3. So similarly, if this made sense, we could write the infinite thing using all the primes, which of course is infinity, so it's a bit pointless, but bear with me. So product. So if you could write this, if this thing makes sense, then it would be equal to the sum of all the possible natural numbers exactly once, because that's what the fundamental theorem mathematics says, right? That every natural number can be expressed exactly in one way as a product of one factor from each of those things. So these would be equal to the sum of all natural numbers. Of course, both sides are infinity, so that's a bit pointless. But if we do the following trick, if I put a power of the -2 everywhere, this is still true, right? And by analysis 1, we know that this converges. So this is not trivial now. And what you get basically is that this is equal to the sum of all the inverses of the squares. But of course, there is nothing special about it. In fact, we know that this converges. So by analysis, we know that this converges for every sigma, with the only assumption that the real part of sigma is larger than 1. So to write this again, basically what I'm saying is that if I have the sum of all the 1 over n to the s, which is 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, so on, this is going to be equal to the product, this here means product over all the primes of the factors of the form 1 plus p to the minus s plus p to the 2 minus s and so on. This, of course, is a geometric series. We know how to sum this. So you end up having this. And if you think about it, the fact that this thing can factorize like that is basically equivalent to the fundamental theorem of arithmetic. So this is a way to express the fundamental theorem of arithmetic in one single equation. We denote this thing by 0. Again, it's important to note that for now we have that the real part of S is larger than 1. Remember from your analysis class that if the real part is larger than 1, then this thing converges absolutely. And this is what they call an Euler product. So obviously this was discovered far before Legendre thought of Primary Theorem, because Euler was a little before that. So basically Euler was thinking about it mostly in terms of analysis. And we're going to need to get a bit more involved to actually do much number theory. But actually you can find some very interesting applications in number theory from that alone. So let me remind you what square free numbers are, so that I can show you a very cool application. So square free numbers are the ones that don't have any square divisors other than 1. So 1 is square free, 2 is square free, 3 is square free, 4 is not square free, 5 is square free, so on. 12 is not square free because it has divisor 4, and so on. And the question is, if I choose one natural number at random, what's the probability that that is equal to that's a square number? And the answer, because of this equation, I'm not going to do the exact calculation, but because of this equation, turns out to be 1 over z2. So this is the probability that if I choose a number at random, square free. And I know that there is no uniform distribution in the natural numbers. So what I mean here, the probability, basically you take the uniform distribution in the first n numbers, you find the probability, and then you take n going to infinity. So that's the probability. And we know, for example, by some Fourier analysis, maybe you've seen it before, that this is equal to pi squared over 6. So again, remember that this is this sum here. So this is equal to pi squared over 6, which means that the probability that a given number is square free is 6 over pi squared. In particular, this means that there are more square free numbers than non-square free numbers. So this is a bit less than 2/3. So actually the probability that the number is square free is about 2 times the probability that the number is not square free. Okay, so this is a very nice application in number theory without using any further, at least not any further related analysis. We're using the Fourier analysis there for the pi squared over 6, but yeah. So this thing is supposed to encode the fundamental theorem arithmetic. And that's the kind of stuff we do in analytic number theory. We take an arithmetic property, like the fundamental theorem of arithmetics, and we encode it in some analytic function. So this is basically just a function from real part of S larger than 1 to C. And it's a holomorphic function there. So it's proper analysis. So what we hope to do is that if we find some other properties of this function, then we can decode them back and get some properties in number theory. So what we did, we took the fundamental theorem arithmetics and we encoded it in something analytic. And what we hope to do is to prove something about the zeta function and then go back to number. I guess you have a product there. So a very natural thing to do if you're working in analysis is to take the logarithm because sums are easier to work with than products. You have logarithms, so another natural thing to do is to take the derivative. So if you take the derivative, this is going to become basically a sum of geometric series, which we can substitute and get moving to the explicit calculation. But this is going to be basically the sum log p over p to the I for I from 1 to infinity. So if we take those two sums together, what we get this thing, where lambda here is just a fancy way to say that this is going to be log p if n is equal to p to the I for some prime p and some I and zero otherwise. Okay. And it turns out that the prime number theorem is equivalent to showing that the sum of those lambdas up to x is asymptotically x. So in particular, there is a way to relate this difference to this difference. Yeah. Li of x is this thing here. It's called Li because it's the logarithmic integral. So if I find information about this difference here, I can translate into information about the error term here. So our strategy is going to be to try to prove this thing. Of course, so far we haven't used any complex analysis, which is the essence of analytic number theory. Yes, now is the time for that. Okay, so people were trying to prove the prime number theorem for about 100 years. The idea of using the zeta function was around. It wasn't like something revolutionary that we used that at the end. But we didn't have enough analysis for that because okay, that's an analytic function, but I mean its definition, it's very number theoretic. It's not truly satisfying to say that this is something that you can study only by analysis. So it was Riemann who came and thought that there is a very nice way to think about this in terms of analysis. So Riemann was not a number theorist. Riemann never worked in number theory. And Riemann was known for differential geometry and complex numbers. As you know, different Riemannian geometry or Cauchy-Riemann equations. So Riemann made only one paper in number theory. And that was a revolutionary paper. So that paper was basically the beginning of all modern number theory. And it's really weird that it came from somebody that's not a number theorist. So it's his only contribution to number theory, but it's basically the most important paper in all the history of number theory. I guess together with Dirichlet prove that there are infinitely many primes in arithmetic progression. Not sure why I made the line. Okay. So before explaining what Riemann did, let me first remind you something from your analytic, from your complex analysis course. So, for example, we know from high school that if the modulus of S is smaller than 1, then this series here sums to 1 over 1 minus S. Of course, this is defined only for modulus smaller than 1, but this here is defined for S smaller than 1. We call such a function an analytic continuation. So this is an analytic continuation, we call it AC, of 1 plus S squared plus S2. So we have analytic continuation in real numbers as well, but it's a bit boring. In complex numbers, what makes it interesting, it is unique, which means that if I give you another function, let's say if I tell you that for the modulus being more than 1, I have another formula for this thing. I don't know, f of s. And this thing is also defined for s not 1. Then I can conclude that those things are equal everywhere. So not only in this region. In other words, if two analytic functions are equal in a small region, it means that they are equal everywhere. So for example, if I have a formula like the Riemann-zeta function, and I find two different formulas for it that can be extended, then I can equate them with each other. You can get more results about that function. And basically, that's what Riemann did. So Riemann came and proved that the zeta function has an analytic continuation. And also, he proved that it satisfies what we call a functional equation. I'm not going to explain what the stuff here are, but there are some very easy functions. It's not something very weird or something. We know like how to study those factors here, just ignoring them because exactly because they're trivial. They're just too messy. So remember that we have a formula for the function that works for real part larger than 1. Which means that if we use this equation, we can basically find a formula that works for real part smaller than 0, right? Because we can use it to reflect. So here is the imaginary part of S, and here is the real part of S. Be careful that this is just the domain. It's not the full function. It's not z of S in respect to S. It's just imaginary part of S and real part of S. So this is supposed to be mapped in another plane. Okay. Here is 1. So I guess it's better to make this. So if I have a formula to work with to find Riemann-zeta function in here. So this region is not that helpful in the sense that it doesn't give much non-trivial information. Using that formula there, we can use a reflection to get this region here. So, for example, if I want to find the value at the point -1 plus I can say that -1 plus I is equal to blah blah z2 plus I, right? That minus. So this functional equation helps us to find the values of Riemann-zeta function in here. Again, this formula here works only for real part larger than 1. And what Riemann did, he found that there is a larger function, but it's equal to this smaller function. And now we're trying to find the values of that larger function. So we can find the values in here. And this part, the thing left, is basically the region where non-trivial things happen. And this is what we call the critical strip. So what else? Okay. One thing that we're interested in, if you remember from your complex analysis course, you have the intuition why we're interested in those things, are the zeros and the poles of the zeta function. So the poles are actually easy to find. There is only one pole here at one. So there is a simple pole here. But what about the zeros? So what about sigma such that z of sigma is 0? Obviously, we don't have any zeros here because if you plug in s here, you always get something non-zero. So what about others? Sorry. So we said that we can translate this region here. So one could be quick to say that there are no zeros here, but we also have this factor, which could be 0 for some s. So it turns out that this factor is 0 for some s. In particular, it's 0 for s being equal to minus even numbers. So the zeta function is 0 at the minus even numbers. And that's what we call the trivial zeros. We can also use this to find the values at the negative odd numbers. I'm not going to write the formula, but there is an exact formula. And in particular, something that you've seen before is that z of -1 is equal to -1 over 12. So I guess if this formula was correct for every s, and if you plug in -1 in here, then you would get 1 plus 2 plus 3 plus 4 and so on. So there is this mean that says that this is equal to -1 over 12. Basically, this is what the mean is about. But it's not correct because I mean it's only defined for real quadrats larger than 1. Just the analytic continuation that it's -1 over 12. Yeah. So yeah, now you know what that mean is about. So,
sorry, do you mind if I just take a picture of that?
okay, yeah, sure. Yeah. Okay. So now let's remember of the formula we proved before. I don't want to erase the graph, but I need to erase the graph. So I will draw it again. Okay. So let's remember the formula we had. This one. And remember that lambda of n it was log p for n equal to prime powers and 0 otherwise. So using some complex analysis, which again I'm not going to do, sorry, for people that it's the prime numbers in the distribution of it. Of course, you've probably seen the proof. But using some complex analysis, in particular considering the integral of this thing. Okay, basically there is this formula called Heron's formula, which can relate this to the sum of lambda n, where here you have some region appropriate. Yes, it's just a line of the region. So in general, what this formula plus error, let's not forget what the error. And I guess there's a factor here also there. So what the formula says in general is that if you have a series an over n to the s, here an is lambda n, and again some appropriate limits, some appropriate factor, which is probably just 1 over 2 pi I, but I'm not sure, so let's not bet about it. So this is if you have some reasonable assumptions about the ANs, you get that from that. So this is what you'll find here. And using some complex analysis, you can get, I'm going to write it again. So, here. Using some complex analysis, in particular, using a Cauchy integration formula. I guess if you remember one thing from your complex analysis course is this. Well, using the Cauchy integration formula, you can rewrite this in terms of the poles of this thing here, right? Using a recipe theorem. So what you get is this very nice formula here. You get that this sum, which is something completely number theoretic again, it's just the sum of logarithmic prime numbers. So there is no analysis going on, I guess, except from the trivial part where the logarithm here, but okay. So this is equal to x minus log 2p, 2 pi, minus log of 1 minus 1 over x squared, minus this term here. So in particular, this is an exact formula. There is no error term. Here you have something number theoretic. Just have a sum of something related to primes. And here you have something completely analytic. So you have x, which is the main term that we hope to prove that's the main term. Then you have minus log 2 pi. Then you have this weird logarithm. And then you have the sum, which is the only non-friendly term. So this is the sum over all the zeros of the Riemann function that are non-trivial. So again, the trivial ones were the ones given by that factor, which were just the minus even numbers. So non-trivial are basically the zeros in the critical strip. I'm going to draw that again. So critical region. So every zero here is called non-trivial. Okay. So this is what we call the explicit formula. And it's, I mean, if you really understand what it says, it's basically one of the nicest formula in all number theory, because it has something completely number theoretic and it's equal exactly with something completely analytic. There is no error term, no approximation, no nothing. Something number theoretic and something that has nothing to do with number theory. Now, let me just explain where each of those terms comes from. Let's remember that this came applying Cauchy integration formula on this thing here. You can see that the poles of this are the following. We have a pole at s equals to 0, a pole at s equals to 1, and s equals to minus 2k, the zeros of the success. And we have also the non-trivial zeros. Okay. So by Cauchy integration formula, this thing here came from s equals to 0. This came from s equals to 1. This was from summing all the terms s equals to minus 2k. And this obviously is from s equals to 1. Okay. So this was proved by Riemann. This is basically the conclusion of his paper. And we can see that those two terms here, this one and this one, are pretty small. So I guess the only obstacle we have in proving that this is approximately equal to this thing is this term here. So this term here is the only problematic one. But we can remember that the modulus of this thing is just the modulus of x to the power of the real part over the modulus of r. So in order to control how large it becomes, we need to control how large the real part of r becomes and how large the modulus becomes. So what Riemann conjecture? So Riemann conjecture, this part. Riemann conjecture that this is Riemann hypothesis. The title character. Riemann hypothesis says that every non-trivial R with zeta part equals to 0 has real part of R equals to half. So this is a Riemann hypothesis, but it says basically that all the zeros of the Riemann-zeta function here must lie on this single line. I mean, there is no evidence, like no obvious evidence for that. It's basically just the best case scenario if you think about it, because if you have a 0 in here somewhere, not here, by this formula you must have a 0 here. So if there is even 1 0 node on the on this line, you get a term that is larger than square root of x. But in the case of the Riemann hypothesis, all of those terms have ordered approximately x to the half. So actually, you can show that the Riemann hypothesis is equivalent to the fact that this thing is smaller or equal to, say, 100 times x to the half times log x squared. This is a pretty good error term. I mean, it's approximately the square root of the main term. So this is equivalent to the Riemann hypothesis. Okay. But even if we don't have the Riemann hypothesis, we can still get many results about primes just from this equation. So, for example, or for the zeta function the other way. For example, you can see that this part here is not continuous, right? Because it jumps each time you find the prime jump. So, if I draw the graph of sigma of ln up to x in terms of x, up to here, okay, it's 0. Then it jumps at 2. It jumps at log 2. Then at 3, it jumps at log 2 plus 3, and so on. So this is not continuous. If we only had finite element terms here, this thing would be continuous. Obviously, you can't have something non-continuous equal to something non-continuous, which means that we have infinite elements here. And just like that, we proved that the Riemann-zeta function has infinite many zeros. We don't know where, we don't know how they look, but just because this would be continuous if we didn't have, we know that they're infinite many. Okay. So, of course, what we were talking about was the prime number theorem. So the only thing that we want to show is that this thing here is smaller than x for x large number, or I guess much more than x. To do that, it's not necessary to prove the Riemann hypothesis. The only thing we need is to show that either the modulus will be large or the real part will be small. So this is what Riemann did. But then we have, as I told you, those two guys who proved the prime number theorem. What those guys showed is that there is this region. I'm not sure why I erased the diagram. Keep doing the mistake. So there is this region here. That. Obviously, it might have symmetric, but not that with graphs. Whatever. So there is a region like that here, called the zero-free region, where the zeta of s is a non-zero here. So this is called a zero-free region. Sorry?
There was a seagull zero.
So yeah, seagull zero is basically a zero that is not on the critical line. So even if you have like a zero here, it would still be a seagull zero. Or I mean, more specifically, a seagull zero is like a term that we use for the zeros that are not good enough for us. So if you are trying to prove a result that needs all the zeros to be in this region, a sequel zero would be zero here. So yeah, what we prove here is that in terms of prime number theorem, there are no sequel zero. But if you are thinking about another theorem, sequel zero can mean something else. Okay, so zero for region. In particular, let's see. So if you are up here, yes, the real part is large, but the modulus is large as well, so we're fine. And if you are down here, then the real part is small, and we don't care about the modulus. So overall, those terms are going to be small. And that's how they prove the prime number theorem. So using this region of region, it's enough to find that this error term is small and that the prime number theorem holds. So we have this theorem here. And this basically was how analytic number theory was born. Erase a few things. So basically, studying the non-trivial, the zeros of the Riemann, the non-trivial zeros of the Riemann hypothesis is the same as studying this difference here. Those things are trivial. Of course, if we prove some other results about those zeros, not inside the Riemann hypothesis, we still can get some nice results about primes. And that's what people do nowadays. I mean, we gave up trying to actually prove the Riemann hypothesis. I mean, every time that a new method comes up, we try to prove the Riemann hypothesis with it. But the main attention is to prove some weaker versions of the Riemann hypothesis. So, for example, we know that there are infinitely many primes, infinitely many zeros on the critical line. So not only there are infinitely many in the strip, but on the critical line. We know in an exact sense that more than 41% of those zeros are on the critical line. We also know that if you take, keep erasing this graph and keep drawing back. If you take a very, very narrow region around this thing, as narrow as you want actually, like epsilon narrow, then and you select a zero at random, then the probability that lands in here is 100%. This is not the same.
100% like measure one.
Yeah, measure one. That's one. Okay. Why that doesn't mean that everything is on the okay. So think about the numbers of the form 1 over n. If I give you, if I tell you to pick one of those numbers at random, then I give you a very small interval here, then the probability that this number lies in here is 1, right? And because all the numbers but just a few lie infinitely close to 0. But that doesn't mean that they lie at 0, right? So that's the same thing here. Just means that they get more and more dense as you go towards the line here, but that doesn't mean that they're actually on the line. But this is good enough to prove many theorems. So such theorems are basically what we call the statistics of the Riemann-zeta function. And to prove them, for example, one thing that we do is we study the the moments of the zeta function. This is things of the form of the zeta function on the line test. So things like that, or for some other real part instead of half. And by probabilistic methods, you can know that this thing is related to the distribution on that line. Actually, it's a bit counterintuitive, but the larger this thing is, the more zeros we can have in the region. This is a bit weird because you expect that a large thing would have less zeros, but let's remember that in complex number, large means many directions. So it's not that weird. And to understand that, let's think of polynomials. So we know that a polynomial, if it has a large degree, so a polynomial larger degree means more zeros, right? So it's similar here. The larger the moments, the more zeros you have. There is currently lots of research on those things, not necessarily with zeta here, maybe with some other versions. The conjecture that we have is that this is equal to, I remember, t times log t to the k squared. Yeah, that's correct. So this is the conjecture that we have, is not proved. We know that for k equals to 1 and 2. And using those things, we can show, for example, that, I mean, not just those things, some expression as well, but there is always a prime between n and n plus n to the 0.525 for n rational. Right? So if you think about it, this is just saying that p of n plus n to the 0.525 minus p of the n is positive. So as we said, it's we can translate this into facts about zeros of the zeta function. The conjecture is that there is always a zero between n and n plus square root of n. If we know the Riemann hypothesis, we can prove that, but with current tools we can't. So
or like three-dimensional, why is it like 41%? Where does that number come from?
to be honest, I've never seen the proof. Sorry. I only know the number. It's one of those that I just know them. But I would say that it's for this term to be small enough. Okay. Also, oh, by the way, those things here are constants. there are constants depending on k, and we actually have some conjectured values for those constants. So one of the latest ways that we are trying to think of the Riemann hypothesis is it turns out that you can relate the zeta function to some random matrices. So these are matrices with random elements taken from a distribution, specific distribution, and you can see that the eigenvalues of those matrices are related to the zeros of the zeta function. It's not proof. It's like we did the calculations and they seem like extremely close. So one thing that people do is they try to prove the same result, but instead of zeta, you use those random matrices, and that's where those constants here come from. And for the values that we know, they're actually confirmed that we have the correct answer. So that's actually one of the hopes that about proving the Riemann hypothesis that still exists, that are still there, like using random matrix theory. Okay.
It's 106.
Okay.
And we can.
So for the rest of the time, I'm going to talk to you about some so let's remember how we ended up with those things. We started with the fundamental theory of arithmetics. Then we found an Euler product. Then from the Euler product, I guess we also found the functional equation. There is some arithmetic intuition why we had the functional equation, but I'm not going to go into that. Combining those two, we got an explicit formula. From the explicit formula, we got a zero per region. And then we combine those two to get the prime number. So basically, the only ingredients that we wanted was the fundamental theory of arithmetics and this functional equation thing. This basically, it's a bit harder to explain when we expect to have that. So let's focus here. So in particular, this means that the numbers are written in a unique way as prime powers. But we have other things that can be written in a unique way as product things. And since we didn't actually use that, it was not essential for the proof that the natural numbers, there is no reason not to expect that other things that could be factorized can give similar results. So for example, we have polynomials that can be factorized into irreducible ones. Right? So and so on. So this is something similar. Every polynomial with integral coefficients can be written as a product of irreducible polynomials in a unique way, right? So you can think of those irreducible polynomials. Irreducible means that they can be not go further. you can think of this as the primes in this example. So, do you think of the irreducibles as primes? We also know that this is still true if you're working in modular arithmetics. So, if, for example, I have some written down, so I don't find. Yeah. So, for example, if you have this thing, this still makes sense, and it's still, you can still consider this as irreducible. It's basically polynomial modulo some prime. So similarly, you can define a zeta function for polynomials modulo primes, which uses the fact that every polynomial can be written in a unique way as a product of irreducibles to make that zeta function have an Euler product. And you can use this exact thing to try to prove something similar to Primary Theorem. And actually, the conjecture, what we could think is that maybe you can also prove the Riemann hypothesis, like a corresponding Riemann hypothesis, that zeta function has all the zeros here. And that was actually proved. So we do know that that zeta function related to polynomial model primes is true. So we know that that Riemann function, the Riemann hypothesis, that zeta function has only zeros on the trivial line. This is what we call Riemann hypothesis for function fields over So this thing was proved, and one very nice application of this, if you did a course in elliptic curves, it's going to sound familiar. If you have this equation here, for example, mod P, where P for various reasons is not 31, and you can show that the number of solutions modulo P, of course, minus P plus 1, take the absolute value of this. This is always smaller or equal to 2 times square root. And the reason for that is that this square root here is basically because of the Riemann hypothesis, of this Riemann hypothesis, the one that's proved. So in the same way that I told you before that we hope to have that P of pi of x over minus lambda x is smaller or equal to 100 times log squared. So we said that the usual Riemann hypothesis would give this result. Similarly here, the Riemann hypothesis gives this result. It's the equivalent thing. Of course, we don't need to stop there, right? There are other things that happen. So, for example, we have this thing called the Gordan integers. Probably you've seen that in some course. So those are numbers of the form a plus bi, where a and b are integers. Those two can be written as products of primes, where prime will mean the obvious thing. For example, yeah. So, for example, this number can be written as product of those two things, and you can see that those two things cannot be written as product of other things. Factors of the form 1, minus 1, I, and minus I don't count as factors. So if you define primes in that sense, so numbers of that form that are not products of other terms of that form, this the equivalent of the fundamental theorem of arithmetic still holds. So you can define a zeta function on that, where you have a plus bi. I guess you don't allow plus minus products, okay? A plus bi, where you get integers, and I guess we don't want the 0, 0. And we do the exact same definition as in the normal zeta function, but instead of the actual thing, we put its modulus. So you have this thing here. And as you can guess, this has an Euler product by the fundamental theorem of arithmetic for Gaussian integers. So using this exact sequence here, you can end up with the prime number theorem, which says that the primes here satisfy something like that, but they're approximately LIX primes up to modulus x. And if you know a few things about Gaussian integers, you can translate that into the fact that there are approximately equally many primes modulo 1 modulo 4 and 3 modulo 4. So the number of primes which are equivalent to 1 modulo 4 are approximately the same primes. 1 to 3 modulo 4. And if you know the numbers with this, obviously you don't need to stop in the Gaussian integers. You can do the same thing for every number field. If you don't know the number field, it's okay. And using the corresponding prime number theorem, you can use the more general thing that if you have like modulo p, the primes are equally distributed modulo in the possible classes. So like, for example, modulo 7, you have approximately equal number of primes, 1 modulo 7, 2 modulo 7, so on. So this is a consequence of the prime number theorem there. And obviously, we hope that we have a Riemann hypothesis here as well. That's not proof. If we had a proof for that, it would give a proof for the Riemann hypothesis as well. No.
How should what will be the one of two? Was that the norm?
Sorry, can you repeat?
Like you mentioned that we can construct like some Riemann hypothesis for Gaussian integers.
Yeah.
So how would that look like? For example, like the real part be half. How would that look?
The real part of S being half.
Oh, so that's the same.
Yeah.
Oh.
I'm not sure what you mean.
Oh yeah.
Oh, by the way, you can rewrite this in a very nice way. I'm gonna erase the order for that. But if you think about this, this is just the sum of 1 over a squared plus b squared, yes? So if you group all the terms that have the same a squared plus b squared, this is basically the sum of Rn over n to the s, where Rn is the number of ways to write n as a sum of two squares, right? Because if I group all the terms that give the same answer here, what I end up is a term which says how many numbers give n. So write this. That's it. So if I group all the if I group for every n, if I group together all the a's and b's that give n, right? So I separate the terms according to what's this sum here. I get this. Then how many terms we have here? Exactly in how many ways we can write n as a squared plus b squared. And this is related to what we call the Gauss circle problem, which is basically approximating how many integers are in a given circle. Okay. So we have stuff like that, but of course we have many other things to factorize. I'm going to give you another example. This is closer to my work, to be honest. So if you consider SL2Z, which is the, let's call this gamma, which is the group of matrices of integer elements that have determinant 1. There is a way to define primes here. I'm not going to explain how you define the primes, but if you define the primes, and there's also a way to define the modulus of this thing. Again, I'm not going to explain that. But if you do that, you get what we call the self-representative function. Which I'm going to write. It's actually not. It's the sum over some cosets of gamma, but I'm going to write it like that. Where again, n is some kind of modulus I'm not going to explain, and which again factorizes into primes. Where again, I'm not going to explain on the same side. And again, we can do the exact same proof of the Primary Theorem to get the corresponding Primary Theorem here. So the fact that number of gamma such that n of gamma is smaller or equal to x is approximately Li of x, which is approximately x of x. And this is what we call the prime geodesic theorem. Now, why is this called that way? Have you seen any Riemannian geometry? if you take the upper half plane as the model of the one-dimensional hyperbolic plane, complex space, you have that these classes here correspond to geodesics. What are geodesics? They are the paths between 2 points that have the minimum distance. So in hyperbolic geometry, if you want to go from here, the closest way is not a straight line, is this curve here. And this basically counts lengths of geodesics. A way to see that is basically that all the rational numbers here can be written in the form gamma dot infinity, where gamma is some matrix of this form. So that's how geodesic comes. That's how our group comes in the picture. So if you want to connect two rational points, it's like connecting gamma infinity with gamma dash. Okay. Oh yeah, again, we're counting geodesics from rationals to rationals, but that's not something odd. There is a reason for that. I mean, it's basically the equivalence classes of the infinity. So it makes sense anyway. So yeah, we have lots of things that behave like primes that factorize. And for some reason, okay, we know why they all have a prime number theorem, but for some reason, it seems that they all have Riemann hypothesis. We have no idea why. Even for that case, for the case of the function fields, the reason why it was correct does not hold for the general case. We have more Riemann hypothesis. For other cases, some of them are proved. So it seems that there is some fundamental reason that if you have a functional equation and a prime factorization, you have a Riemann hypothesis. But we have no idea why. We believe that it has something to do with random matrices or with operations or with stuff like that. But yeah, some versions of the Riemann hypothesis are actually used in quantum physics nowadays. So it's actually involved in basically everything. If you have factorization, you have a Riemann hypothesis. No idea why. And we did calculations. I mean, we calculate like for the Riemann hypothesis, which, as I said before, initially we didn't have any actual evidence, right? It's just that it's a nicer case. Nowadays, we calculate the first trillion of zeros, and we know that all of them lie on the clear line. There is an algorithm to check if it given zeros on the clear line. I guess if the first x zeros are on the critical line, it's called Turing sample for it. So we have Turing involved in that as well. Yeah. How much time?
It's now 1:30.
Okay.
So she might have over for a Q&A.
Sorry. Oh yeah, sure.
So yeah, if you have any questions, please ask. Shout.
Don't try.
Is prime gas kind of like in any way related to Riemann hypothesis?
Not really. At least not in the way that they study them nowadays. Of course, if you're talking about prime gaps like this one that I took, then yeah. But if you're talking about prime gaps in the sense of 20 primes, then no. And I guess the main reason is that if you try to do this, then the explicit formula is not that sensitive to be able to detect that small difference here.
So would you say that's more like additive? And then here these things are more like.
So basically, prime gaps are mostly studied in C theory, which can be considered as additive, but it's not exactly. People that do C theory many times do additive as well, but I guess, for example, Selberg here is lots of C theory. So yeah, I think it's better to consider it as a third thing. It's multiplied additive and C. Oh, yes. Yeah, any other questions?
And do you have any recommendations for like further reading?
Yeah, I can send you a reading list if you want.
Yeah.
But I would recommend I'm bad with titles. So the standard book in the study of the Riemann function is the one by Teichmann, I think. I don't remember the name. Basically, something like the Riemann-zeta function or something like that. I'm not sure of the title. Something like that. And also some other nice books are Davenport's book, which I can't remember the title. We have Mertz's book, something like Problems in Number Theory. But yeah, I think it's better to just send your reading list. If there is like a way to send it to everybody.
Then you can send via email and I will post it on the.
Okay. Yeah. Oh, and I guess I found part that I forgot to say just for closing. We know approximately how this behaves, but another question is what's the sign of the difference? So is y of x an overestimation or underestimation? So if you try the first, I don't know, trillion or more 10 to the 20 x's, I'm going to find that this is negative. So they believe that it's always negative, that this is always an overestimation. But then Littlewood came and proved that not only it's not always negative, it's oscillates infinitely many times.
Awesome.
Yeah, so it changes sign for infinite times, and that's one of the reasons why. I mean, that's a very nice example of why checking the first millions of cases is not a proof, because like they check 10 to the 20. And yeah, I think we believe that the smallest number for a change is around 10 to the 300. But yeah, and yeah. Oh, and another part, Littlewood to prove that result. The first part assumed that the Riemann hypothesis was true, and the second part assumed that the Riemann hypothesis was false. So he proved it using the Riemann hypothesis and using the opposite. That's a very cool method because you have like Riemann hypothesis has some very cool consequences, and the opposite of Riemann hypothesis has some very weird consequences. So both things give are helpful, and that's a method that we use in other things as well. Okay, that was all.
Yeah. Thanks a lot for this amazing talk, Mario. And I'm sure all of you have learned quite a bit. And right, yes, regarding what I said, yeah, hopefully Mario can send me the reference, and I'll post it on the Instagram page, which is the ucl.unc. If you search it up, it will be the Instagram page. Right, and this time next week we'll be having another talk by Matthew. Hopefully, yeah, and stay tuned. Yeah, thank you.